All right. Hello. This is take two of me trying to record a makeup lecture for Thursday, July 25th. I don't know why I said it was take two because it's not like you're going to see take one, but here we go. So as I said in class, the thing I want to do in this lecture is talk a little bit more about MST algorithms like prims and Kruskal's, and in particular see if I can implement at least one, if not both of them. Uh, and hopefully that uh, is valuable in terms of like thinking about the algorithms a little bit more. Um, so just so you know, I am kind of doing this live. I don't have code prepared for this, so I'm going to kind of try to figure this out as I go. So bear with me if and when I make mistakes. Here we go. Okay, so I figured we could start with prims, right? Basic setup of prims is we start by mark every vertex as unpicked, right? And we're going to build our tree one vertex at a time. So we start by picking an arbitrary vertex, right? And then we say while there are still unpicked vertices, we're going to find the vertex find the, I guess, unpicked vertex closest to any picked vertex, right? This is sort of the greedy part of the algorithm, and then we're just going to pick the vertex that we found. Via the closest edge, right? Okay, this is the idea of Prim's algorithm. Let's start by I guess the first thing that I need is a graph to do this on. So maybe I'll start by like drawing a graph here, and then we can think about a way to input it. Okay, so I might as well start with something similar to a graph that we used in class. So maybe I've got vertices like this, three there. Maybe I've got another two here. Forgive my inability to draw straight lines. And then maybe, I don't know, maybe I have another vertex out here, right, just to make this interesting. So I've got 1, 2, 3, 4, 5, 6 vertices. And then I need 1, 2, 3, 4, 5, 6, 7 edge labels. I am gonna pick, yeah, why not? 8, 6, 7, 5, 3. I'm gonna call this a 1 because I don't want a vertex, or I don't want an edge labeled 0. And then 9. Right? Okay. This is my graph. Let me cool. Okay. Let me go over and put it into a text file so that I can load it in. So we're going to say we have what, 6 vertices, right? We have an edge from, oh wait, maybe I should label these for my own convenience more than anything, to be honest. But here we go. We'll call this vertex 0, 1, 2, 3, 4, 5. Okay. So the edge from 0 to 1 has a weight of 8. The edge from 1 to 2 has a weight of 5. The edge from 2 to 4 has a weight of 3. The edge from 3 to 4 has a weight of 1. The edge from 1 to 3 has a weight of 7. The edge from 0 to 3 has a weight of 6. And the edge from 3 to 5 has a weight of 9, right? So that's 7 edges. 2, 3, 4, 5, 6, 7. Perfect. Yep. Okay. So this is my graph. And this is what I'm going to use as an example. Let me clear the annotation. Yeah, because we can always redraw this. Okay. And let's start just a I don't know. open this in read mode, and then we can say while scanf from the file pointer. Oh wait, I guess we start by saying vertices and then read the number of vertices. So that's just going to be an integer into number of vertices, and then we'll say so source, target, and weight. Okay, so sort of lay this out. This is obviously not going to compile, but now I suppose I need a graph data structure somewhere. Prim's algorithm, I care a lot more about outgoing edges than I do about knowing whether a particular pair of vertices is connected by an edge. Like I am more likely to start with a source vertex and then look at edges going out. So I think we can use an adjacency list here, right? So we'll make graph.h. Let's go ahead and construct graph. Graph is going to keep track of the number of vertices, and then how should we do this? We should maybe have an array of edge lists, right? So maybe I'll make struct edge list. And this will have edge, we'll have int source, int destination, and int weight. And then an edge list is going to have I guess we don't need the source because we can, yeah, okay. Edge list is just going to have a pointer to an array of edges. Maybe we can say this to make it easier to dynamically resize things, right? So we've got this, and then we've got struct edge list. Lists, I don't know, whatever. Right, so each edge is going to go in a particular position in the edge list, which will represent the source vertex, and then each edge is going to have its destination and the weight along that particular edge. Our list of edges, or our edge list, is going to have a pointer to an array of edges, and then we're going to keep track of the number of things in that array and the current capacity so that we can dynamically resize it if we need to. And then same thing, graph is going to know the number of vertices, and it's going to have an array of edge lists, and this is going to be maybe I'll say it's an array indexed by the source vertex, right? So I guess the first thing I need is an init function, right? And then maybe I'll say void graph add edge. This takes a pointer to a graph. This takes a source, a destination, and a weight. I guess I'm spelling destination with an E, so I'll keep doing that. And this inserts an edge. I think that should be all I need for now. Let's make a C file to implement this. So I'll include graph.h. I'll grab the functions that I have to implement. Go. And then I'm going to need malloc, so I'll start by including standard lib. Right. Okay, so for graph, I have a number of vertices, and I allocate an array of lists. So I say A, and G is what we're going to return. I can say G pointer to num vertices equals num vertices. I can say G pointer to lists is going to be, we're going to struct edge list array, and then C alloc The count is num vertices. The size is size of struct edge list, right? So I store the number of vertices that I have, and then I build an array of edge lists. Oh, and I guess I need to initialize an edge list here as well. So maybe I'll just say, right? This is going to start empty. So maybe we can use like a constant initial capacity. Of 8. No good reason for that. It's just what I picked. So I can say edges equals, let's build an array of size, initial capacity, and size of each element is the size of an edge. We can say capacity equals initial capacity, and then num edges equals 0. Great. And so now I can say for int I equals 0, I is less than num vertices. I plus plus, we can say g lists I equals list init. Okay, and return g. Great. Okay, now to add an edge, I go into, so insert the edge destination comma weight into the list corresponding to source, right? So I can say g lists source. This is the list of all vertices, or this is the list of all edges leaving the source vertex. We can say, I guess I need, oh wait, I need to return list here, right? Struct edge list append. If num, if, oh. Right, so we can say if list num edges is this greater than or equal to capacity? If I've got 8 edges, yeah, if it's greater than or equal to capacity, then I want to realloc, right? Because otherwise I'm going to overflow. So I can start by saying edges equals realloc. I grab a pointer to the original thing, and then I look at the new size that I want, which is list capacity times 2 times the size of a single edge. Right, and then I can mark list capacity as being doubled as well. Now I know for a fact that I have enough space, so I can say list edges at num edges plus plus equals e. And I don't want to return an edge list. I want to just void. Okay, perfect. So here I can say list. I say list append, right? Take a pointer to the list that I want to append this to, and then I build an edge out of destination comma weight. Is he going to yell at me for this? Do I have to cast this? Yeah, I have to cast this. Okay, so we'll cast this to struct edge. And because we're treating our graph as being undirected, I also need to do this backwards, right? So I need to say dest source weight, right? Yeah, just because I'm treating this as undirected. If you weren't, I guess you would only need one of these. Okay, and this should be all I need for adding an edge. Now we should be able to create our graph here. So maybe I can include graph, and maybe I can say graph init num vertices once I've scanned that in. And now I'll say struct edge e. So I'll read one edge at a time, and then I'll say this will go into e dots. Oh, I need a source. Okay. You know what? Let's just do this. Int source destination weight. Right, let's not put it into an edge. Okay, so now I can read the source, the destination, and the weight. So while I still got stuff to read, now we can say graph um, add edge, and I can take a pointer to my graph. I can take the source, I can take the destination, and I can take the weight. Okay, that's easy enough. Yeah. Um, okay. I like this so far. Just to make sure I've read the graph incorrectly, I want to maybe go through and print out the degree of each vertex. So for int I equals 0, I is less than num, vertices I plus plus, print f degree of vertex d is %d. And then we'll take the vertex, and then we'll take g arrow lists I dot num edges. So there's a number of outgoing edges, and this should give me the degree. Yeah. Okay. Cool. Okay. I like this. Let's go into my make file. I'll tell this to compile graph.o, and we'll give it the graph.h header, and I'll call this I don't know, prims. Right. Okay. Okay. So it tells me the degree of vertex 0 is 2. Oh, I guess maybe it was valuable to keep this around. But yeah, that makes sense because I've got 1 and 3 adjacent to 0. I've got 2, 3, and 0 adjacent to 1. I've got 1 and 4 adjacent to 2. I've got 4, 1, 0, and 5 adjacent to 3. I've got 2 and 3 adjacent to 4. And I've just got 3 adjacent to 5. Okay. I'm happy with this. And 0, 1, 2, 3, 4, 5. So it looks like it's read the correct set of vertices. Okay, awesome. So all that just to read a graph. That's fine. We can do this. What comes next? Okay, so we've built a graph. We mark every vertex as unpicked, start by picking an arbitrary vertex. Okay, so let me make prims.c. And how do I want to store the output of Prim's algorithm? Maybe I want to build a new graph where the set of vertices is the same and I just add an edge for each edge. Right? Okay, so let's do that. Let's make a header file. And I'll start by, of course, including graph. And I'll implement a function that does prims MST. And it returns the MST graph, right? Maybe I can close out of these. Okay, now to implement it, let's start with include prims.h. And now let me grab this. Okay. All right, the fun part, right? So we can say struct graph. The minimum spanning tree is going to be graph init. It's going to have the same number of vertices by definition because it spans G, right? So I can just grab G num vertices, and it's going to start with no edges, which is exactly what I want. And now I need to actually implement Prim's algorithm. So maybe it's valuable to move this nonsense into here so I can keep track of it. Okay, so I start by marking every vertex as unpicked. Okay, this means that I need to know which vertices have been picked. So maybe I'll have an array for that. So I'll include standard bool, and then we'll say bool picked. I mean, you know what? I'll just use a dynamically sized or variable length array or whatever. So I'll just say bool picked b num vertices, right? And then can I memset? Can I do this? Is this a thing? Expected 4. What are you talking? Never mind. Forgot this. I'm not gonna. Okay. We'll just start by int I equals 0, I is less than vertices. I plus plus. I will say picked I equals false. Okay, so nothing's been picked, right? Now we might as well start by picking vertex 0. It doesn't really matter where we start, but I'll just start at 0. So maybe I'll do this and I'll say picked 0 equals true. Okay, now while there's still unpicked vertices, find the unpicked vertex closest to any picked vertex, pick the vertex that we found. Okay, so how do I do this? This feels like a Dijkstra's sort of thing, right? So if I pull out my annotations again, right? What I've got going on here is I've got a vertex, right? It's got a bunch of edges coming out of it, right? In our actual graph, these edges are sort of undirected, but for now, I'm going to draw them as directed because it shouldn't really matter. Okay, so I've got a vertex with a bunch of edges coming out of it. Once I pick this vertex, maybe I want to maintain a list of adjacent vertices, so I can maintain like a frontier, right? And the frontier originally starts off empty, and once I pick a vertex, I look at all of its adjacent vertices, maybe X, Y, and Z, and I can put them into the frontier, right? That makes sense. And yeah, and then pick the minimum thing. So maybe this frontier is in fact a priority queue, right? So I can enqueue a bunch of vertices into the priority queue with whatever this edge weight is, right? So call this epsilon. I don't know. The difference between this and Dijkstra's is in Dijkstra's, the priority I would use to enqueue with is not just the weight of the edge, it's the weight of like if I have some source here, right? It's the weight of the path from the source plus this edge. But here I only care about the edge because I only care about picking the smallest edges. I don't actually care about the source, right? But maybe I can use the fact that this like morally feels like Dijkstra's to help me write this. Okay, so it's clear. Turn off annotations. Okay, so I think I'll need a priority queue. I'll need a distances table. No, I don't need a distances table. I need a priority queue, which can hold the distances as well. And then I need I need to know the predecessors, right? Okay, so let's, I'm going to cheat a little bit. And I'm going to steal a priority queue implementation that I made when I was trying to write project 3. Oh wait, maybe I'll cp pq dot, yeah, okay, let's grab that. And then I think, oh wait, let me get rid of the object file. Okay, so I have a priority queue here, which has a bunch of stuff that we don't actually care about for this because it was for that, but I'll set a vertex, I'll say int. I'll get rid of this, I don't need this. I'll get rid of set.h because I don't need that. Include graph. What was I using graph for? That's weird. I'm gonna get rid of that. Okay, so I've got vertex distance, which gives me the vertex and the distance that it has from our set of picked vertices. And then my priority queue has a pointer to a heap and a size, which is the capacity, and then a current load, which is the number of things in it. I have an init function, I have a free function, I have enqueue and dequeue, and then sync and heapify, right? If I look at my implementation here, I can get rid of all of the stuff that I don't really care about. I can get rid of all of this and that and that. Okay, this seems fine. Yeah, okay. So my init function inits it, destroy, freeze all the pointers. I have like a heap sync and heapify, which just syncs everything in the heap. Grow resizes it, enqueue grows if it needs to, puts it into the heap and then heapifies, and then dequeue grabs the last element, like swaps it to the end and then returns it. Cool. Okay. So I've got a priority queue. And I think when I initialize it, I need to tell you how many vertices or how many like maximum things it's going to have. That's just going to be the number of vertices. Right. So now we can say, maybe I can include okay. Include EQ. We'll say we can say, right, or whatever, right? MST num vertices. Okay. So we've initialized a priority queue with that amount of space. I know I won't have to reallocate because I'm never gonna like I'm inserting vertices, so I'm never gonna have anything more than that. And I can start by maybe okay, so I've picked 0, right? So I can start by inserting everything that's adjacent to 0 into my queue. So maybe I should call this like frontier or something like that, right? Because these are the vertices that are adjacent to so I'll comment this. So I can say queue contains vertices, contains unpicked vertices adjacent to at least one picked vertex, right? Now I can say for int equals 0, I is less than, okay, so I need everything, so I've picked 0, so I need everything adjacent to 0. Everything is going to be unpicked necessarily because 0 is the only thing that's picked, so I just need everything adjacent to 0. How do I get that? I say g arrow list 0 dot num edges. So I loop over all the edges here. I++, thank you. Now I can say the vertex that I care about, I guess, like, you know what? Here, instead of this is just going to be, I'm not going to use vertex. I'm just going to use, I'm going to include graph. And then instead of vert dist, I'm just going to say struct edge because it's morally the same, right? It's like, it's an edge is a destination vertex and a weight. So I'm just going to use that. And then I think I need to replace size of struct edge. What is going on here? Oh, because this is struct edge. There we go. And then instead of distance, I'll say weight. Maybe this is more, maybe this is not worth it. I don't know. Whatever. Weight. Okay. Struct edge. DQ the edge. Call it an edge. Whatever. Size of edge. Okay. Did I get all of them? Okay. Let's just like I want to make sure everything still compiles. So I'm going to insert, I'm going to add pq.h and prims.h, and then pq.o and prims.o to my make file. And then we'll make clean, and then we'll make, oh, good, okay. Wonderful. In, there we go. Oh, I don't know why I did that. Nope. Oh, frontier is unused. Okay, that's fine. I don't care. Okay, cool. All right, so we've got a priority queue. Let's do this. And then for each edge, we can just PQ and Q into our frontier, the edge, right? So we can say G lists 0 dot edges at I. Yeah, cool. This is good. Okay, so we can queue all of the edges that are incident to 0. And that gives us all of the vertices that are adjacent to 0 in order of which one's closest. So now I can say while frontier load is greater than 0. So while there's still vertices on the frontier, so like vertices that are unpicked, that are adjacent to something that we've picked, we're going to start by saying struct edge next equals pq dq from the frontier. And then we check to see um, if the vertex that we're trying to DQ has already been picked, then we skip it, right? So if picked next dot destination, continue, so skip. So here we can assume that it hasn't been picked. So we'll start by marking it as being picked. We will add, oh no, oh, oh yeah. Okay. I also need, I need predecessors, right? So I need to know what like I need to know the source vertex every time, right? So I can start by setting maybe preds at I equals -1. So this is just like an unmarked vertex that we haven't looked at yet. And then we can say uh, list 0 dot edges I. This is the edge. So if I look at its destination and I set the predecessor of that to be 0, because I know that all of these edges are coming from 0, right? So I set this as picked. I insert an edge. So I can say maybe graph add edge into my spanning tree graph, right, which I declared up here. And then to specify an edge, I have to tell you oh wait, I just give you a source, a target, and a destination, right? So the source is going to be the predecessor of the edge that I'm looking at. The destination is going to be the destination, and the weight is going to be the weight. Is that not what you want? Source, destination, weight. Yeah. What gives? Oh, yeah, next dot weight. Cool. Okay. So I add the edge. Now I've removed this vertex from the frontier. So I need to add all of the outgoing vertices, right? All of the unvisited outgoing vertex. Unvisited or just any of them? Unvisited. Yeah, unvisited outgoing vertices. Okay. So let me add, what do I do? Oh, okay, so I know, actually maybe it's worth knowing what the source is, right? So int source equals, oh, no, destination is the new one that we added. Okay, so I can say for int equals 0, I is less than g lists next dot destination dot num edges. Okay, so I is another vertex that we might add. We can say, or I guess, then the other vertex that we might add is g lists next dot destination dot edges at I. Okay, what's your problem? Initializing int with an expression of incompatible type struct edge. Well, struct edge, new edge. Okay, thanks. That's the edge that we might add. We check to see if the place that edge would land has already been picked. If picked, new edge dot destination, we skip. Otherwise, we enqueue it, right? So we can say pq enqueue frontier new edge, and then we can set the predecessor. The problem here is we might have two different vertices pointing to the same vertex. And so we don't want to overwrite each other. We don't want them to overwrite each other's predecessors. We want to keep whichever one is smallest. So maybe we keep, okay, if we already have a predecessor, if pred's new edge dot dest is greater than -1, then we check the weight for that one. Is that right? We could do that. Yeah, okay. Maybe it is worth keeping int. Equals, and then let me grab this edge. Dot weight. Okay. So if there's already a predecessor, if there's no predecessor, so if this thing equals -1, or if it doesn't equal -1, if the distance to new edge dot destination is greater than my distance, which is new edge dot weight, then we want to update it. So now we say predecessor's new edge dot destination equals next dot destination, which is the source, and then we can say distances new edge dot destination equals new edge dot weight, right? Okay, so we update predecessors and the distance it has from the set of unpicked vertices. We've enqueued the new edge into the frontier, and this should be good. Now we just keep running this until the frontier is empty. I think this is done, right? I wonder what happens now if I try, let's say maybe I should maybe include prims.h, and then I can say struct graph mst equals prims mst on g, right? Not going to print anything yet. I just want to see if this like seg faults or something. Oh, and it doesn't. Oh, unused variable. Okay, stupid. Okay, print the address of the. I don't really care. Variable length array used. Oh, okay. You know what? I am going to silence some of this nonsense in my make file. Cool. All right, it runs. Let's see if it runs correctly. Let's print out the edges of the spanning tree, and maybe we can draw them and see if that makes sense. Yeah, okay. So for int num vertices plus plus. I only want to put, so every edge is going to appear twice, right? Because it's going to go from like A to B and then also B to A because it's undirected. So I only want to print the edge if A is less than B, right? Or if A is less than, or there's no self loop. So if A is less than B, and that way I only print each edge once. So I'm going to loop over each of these and then say for int j equals 0, j is less than mst lists I dot num edges j plus plus. Then we can say if I is less than mst lists I dot edges j dot destination, print f. So I is the source, j is the destination, edge percent d to percent d. And we'll print I and j. Okay. This should now print out our okay. Okay. Prims. Okay. Edge 0 to 0. I don't like you. 0. Okay, let's ignore the. What did this do? Why did it go 0 to 0 and then also 0 to 1? And then 1 to 1, 3 to 1, 3 to 2. Maybe it's worth printing some things out here. Okay. We can say, and I probably want to include standard io.h. Okay. Okay, start with that. Um, I'm checking next closest vertex, %d, distance of %d, and then we'll say next dot destination, next dot weight. Okay, let's see if this is enough to spot the error. If not, we'll add more print statements. Okay, so we start with, oh, maybe this is going to be worth drawing out. Okay. Like I said, I do not have a working implementation off to the side, so I'm kind of figuring this out as we go. I don't know. For y'all watching at home, I mean, you can feel free to skip past the part where I debug this if you want. Okay, so what did I, 0 to 1, 1 to 2, 2 to 4, 3 to 4, 1 to 3, 0 to 3, and then 3 to 5, right? I started at 0, so I should have two vertices in the frontier, which is 1 and 3. 1, oh, this is problematic. Checking the next closest vertex. Okay, this seems to be an issue because it's pulling. Okay, so obviously 1 and 3 are the like correct things to put in the frontier, but the distance from 0 to 1 is 8. The distance from 0 to 3 is 6. So it should look at 3 before it looks at 1. Okay. Have I messed up my priority queue somewhere? Um, kind of want to just keep this up, but I don't. Okay. Let's look at enqueue, or maybe let's look at heapify. How did I'm comparing the weights. If left dot weight is less than root dot weight. Okay, maybe it's worth printing out the entire queue here, right? When we say that there's two vertices in the frontier, maybe we can say for int I. PQ contains %d, %d. And then this will be frontier heap I dot destination, and then frontier heap I dot weight. And in theory, this should be sorted appropriately, but maybe it's not. Okay. So, oh, cool. This is just sorted wrong. Okay, so clearly my heapify is wrong. Well, that's good to know. That is good to know. Why is my heapify wrong? After I enqueue, I heapify. Okay. When I heapify, I go load divided by 2, so that's 1. So I go at 1, and then at 0, I sync. If left of root, um, yep, okay, so at 1, it shouldn't do anything. At 0, left is defined as times 2. Okay, so at 0, it should look at if PQ heap 1 dot weight is less than PQ heap 0 dot weight, it should swap 1 and 0 and then continue syncing at the left. Okay, that seems accurate. God, am I gonna have to step through this in a debugger? Okay. Let's set a breakpoint at let me start by clearing the annotations just so I can actually see what I'm doing. And then we'll set a breakpoint in pq.c heapify, maybe line 29. Okay, let's do that. You know that's what I meant. Run. Okay, here we go. Okay, so the heap starts at that. Okay, so there's not really anything to do there. So we're done. Okay, cool. Continue. All right, now if I print uh, why are we heapifying so many times? Backtrace, Prim's MST. Yeah. Okay, well, whatever. Continue. Continue. Here we go. Oh, what? Okay, I'm just gonna restart. Okay. Um, actually, maybe I want to start. Let me clear the. You delete a break. Okay, whatever. I don't use LODB. Okay. Maybe I'll set a breakpoint here at prims.c line 36. Run it. Okay. Now let's print frontier load is 2. Keep 0, keep 1. I don't know what I expected that to do. Okay, if we now also set a breakpoint at heapify, rerun. I hit heapify. Okay. Load is 0. How come? Oh no. Did I mess this up? I in Q. Oh, okay. Here we go. There we go. Not the off by ones. Okay, is this any better actually? If I look at this, 2 vertices, 3, 6, and then 1, 8, so it picks 3. Not yet picked. Well, there's 4 vertices in the frontier. Ooh, that's not fun. Okay, so I think the other thing I'm missing is when I DQ, I need to reheapify. Right. Okay. So in. Okay, whatever. I DQ 1, then I pick or I DQ 4 at a distance of 1. Then I pick 2 at a distance of 3. Now I've got 1 at a distance of 5. Okay. Now I skip 1 at a distance of 8, skip 1 so this is sort of the issue, right? Like I've got things in here that shouldn't, I mean, I'm not things might end up in the queue multiple times. But I then pick 5. Okay, so am I at least picking vertices in the right order? If I redraw the graph, the order in which I pick things is, what do? I pick, let's see, 3, 4, 2, 3, 4, 2, 1, 5. Yeah, 3, 4, 2, 1, 5. 3, 4, 2, 1, 5. Okay, if I redraw this graph, I have there's a triangle here, right? And then something like this, and then something like this. So I had 0, 1 goes like that, and then like that, and then like that. So 0 to 1 was 8, 1 to 2 was 5, 2 to 4 was 3, 3 to 4 was 1, 1 to 3 was 7, 8, what was 6? Oh, 0 to 3 was 6, and then 3 to 5 was 9. Okay, so if I pick things in this order, so I start with 0, right? Yep, I start with 0. Then I pick 3, so I mark this edge. Then I pick 4, so I mark this edge. Seems good. Then I pick 2, then I pick 1, and then I pick 5. This is 5. Okay, this seems like a reasonable tree to me because I've skipped the 7, which is good because I don't need the 7. And I've skipped the 5. Yeah, this seems reasonable. Okay, so the only thing, so I'm picking vertices in the right order. The only thing that's wrong is the edges that it's drawing. Why in the world is it doing this? Um, these are going to the wrong place somehow. Okay, but why? For what reason? Let's clear, let's print the weights as well just to see if it's the wrong edges or if it's like the wrong destinations. I could say, oh, yo, it's not J that I want. It's the destination. And then just for fun, let's print the weight and see if it's actually okay. So boom. 0 to 3, 1 to 2, 2 to 4, 3 to 4, 3 to 5. Yeah. 1, 2. Yeah. Oh, that looks good, doesn't it? With a weight of 6, 5, 3, 1, 9, and we've skipped the the wait. Zero to one, 1 to 2. We've skipped 0 to 3, which has a weight of, oh no, we've kept 0 to 3. Hang on, let me redraw this. Okay, so 0, 1, 3, 2, 4, 5. And we've picked 0 to 3, so we've picked this edge. We've picked 1 to 2, 2 to 4, 3 to 4, and then 3 to 5. Seems reasonable. Yeah, so we've skipped the 1 to 3 edge of 7, and we've skipped the 0 to 1 edge of 8. Yeah, okay. That's good. That's really good. Okay, I'm happy with this. Great. That's Prim's. I'm satisfied that this is the correct answer. I hope you are also satisfied. This took longer than I expected. So I'm gonna call it here and maybe make a separate video with cruise calls because cruise call is gonna take so long. Um, See ya.